Okay, so I am going to talk today about the quantum approximate optimization algorithm, and I'm going to try to talk about some recent stuff. I'm going to first give an introduction to what the QAOA is, try to explain what it is, and I have a lot of recent results, so we'll see what we get to in the course of my time here. And this is really an attempt to use quantum computers to solve optimization problems. And people are very skeptical about the ability of quantum computers to solve optimization problems. But I think that skepticism is only prejudice. It's not based on anything other than a belief that quantum computers can't do things classical computers can't do. And so I'd like to take an optimistic point of view and talk about my own stuff, okay? And my affiliation is Google. I am a full-time Google employee. But I still hang out at MIT. I'm based on the East Coast because I was many years at MIT. So I'm going to talk about combinatorial optimization. And here, the idea is this. We have bits, n bits, and we have clauses which are constraints on subsets of the bits. So a clause might say, if I look at the first two bits, I'm satisfied or happy if they disagree, but I'm sad or unsatisfied if they agree. So a clause is a constraint on a subset of the bits, okay? And I'm going to assume that my problem, whatever it is, the instance of my problem has m clauses, and I labeled them by C sub alpha, Z. Z are my bit strings, which go from 1 to n. And note that C alpha of Z is either 1 if it's satisfied or 0 if it's not. In this talk, I'm going to be going uphill. I want to improve this function C. I want to satisfy clauses. So if I give you a set of clauses, I give you, let's say, 1,000 bits and 2,000 clauses, the goal is to find the string which maximizes the number of satisfied clauses. And often this can be very challenging if the clauses contradict each other in some way. You can easily imagine 3 clauses which cannot be simultaneously satisfied. So the goal is to find the string that maximizes the number of satisfied clauses. And the goal for us in approximate optimization is to find a string such that the string Z has satisfied C of Z clauses, but that number divided by the maximum number that could be satisfied is big. Now, if you could guarantee, if you had a polynomial time algorithm that could solve this problem with an approximation ratio of 1, then P would equal NP. This is like the mother of all computational problems trying to optimize this. Okay, so any questions yet? So what we're going to try to do is look at this with a quantum case and try to make this thing called the approximation ratio big. And we'll talk about how big in a minute. So I'm going to do this with a quantum algorithm. And the quantum algorithm has certain ingredients, but I should be clear here. We're going to work in a Hilbert space, which is spanned by 2 to the n basis vectors, which I label Z1 to Zn. So there are 2 to the n basis vectors, where Z is, sometimes I let it 0 and 1, and sometimes it's 1 and minus 1. I promise I'll confuse you with that. But, so this is the Hilbert space is spanned by these basis vectors. And the my clause function can also be viewed as an operator, where C on Z, let's think of it as the cost function value times z. So let's just read that equation. That says the quantum operator c, acting on the basis vector z, is the value c of z times z. In other words, this cost function, I call it the clause, but the cost function operator is diagonal in the computational basis. Now, if it's diagonal in the computational basis, so is e to the minus I gamma c, which is the exponential of it, which is a key ingredient in this algorithm, the exponential of the cost function with the parameter gamma. But note that since the cost function is a sum, I can also write that as a product over the individual clauses. So that's very convenient for us to write it as a product. I lost my pointer, okay, big deal. That's just the beginning of my problems, okay. There we go. And I have another operator, b, which is the sum of the sigma x's. And note, the exponential I'm also going to use the exponential of the b operator, which can be written like e to the minus I beta xj. And note that what these things, each of these is a rotation about the x direction of the individual qubit. This rotates the qubit by angle beta, and this is rotating for 1 beta, all the qubits simultaneously. Okay? And I also need, if I'm going to run a quantum algorithm, I need an initial state. I have to start somewhere. And the state we're going to start in is the uniform superposition of all possible input strings. And note that that's a very easy state to make. It's a product state. And the reason you can see it's a product state is consider 1 qubit. And consider this thing called the plus state, which was already discussed today, which is the eigenstate of sigma x on 1 qubit. It's 1 over root 2, 0 plus 1. But if I take 2 of them, or 3 of them, if I have 3 of them, I have all possible combinations of the 3 bits, 0, 0, 0, 0, 0, 1. So this thing is actually the product of the pluses for each qubit. And so it's easy to initialize that because all you have to do is line your spins up in the x direction. So now what we're going to do next is for any integer p, we're going to pick p betas and p gammas. So the p, so we pick, these are all angles because actually in this case, because each of the sigma x's has eigenvalues 1 and -1, and the clause thing is integer valued. So the exponential of it is, if gamma's if you add 2 pi to it, you just get the same thing. So gamma and beta, these are angles. And so I'm going to define a quantum state, gamma beta, where I act with the cost function unitary with angle gamma 1 on S, and then I act with the rotation about the x direction with beta 1, and then I go to 2, 3, up to p. So it's a sequence of simple to construct unitary operations, and I have 2p parameters. We call this depth p. And so we're defining the depth as be one operation of these 2 operators. Okay?
The rotations are uniform?
I'm sorry?
The rotations around x are uniform?
Yeah, everyone's the same.
Just one angle or
one angle. We could talk about why that is. But yes, that's what I'm starting with. Now, note that I can define something fp, which is the expected value of the cost function in the state gamma beta. Now, let me just tell you the idea then. The idea is going to be to choose gamma and beta to make the expected value of the cost function big. And if you can find the gamma and beta from which the expected value of the cost function is big, then if you make a measurement, let's say, in the computational basis, you're going to get a string with a good value of the cost function. So the whole idea of the algorithm is to find parameters, gamma and beta, that make this big. Okay? Now, so for any fixed depth p, I can define the maximum over gamma and beta of this function. It's just a mathematical definition. But note that if I go to one higher level, I can only make the maximum bigger. And that's because if I'm a level p, and I set the last two parameters to 0, I get the algorithm at level p minus 1. And you can view that as a constrained optimization at level p, where I've set the last two parameters to 0. So by loosening that, it can only go up. All right? So this is clear. But we can also prove that if you fix the size and you take the limit as p goes to infinity, there will be parameters such that this actually achieves the maximum. Now, that is true mathematically, but it's not necessarily useful because it may be the case that in terms of the size, p has to be, let's say, doubly exponential in n. So, but it's a true mathematical statement that this algorithm will only improve with depth, and if you go to infinite depth, it will achieve the maximum.
It will output a pure state, a pure assignment, right?
No, it'll output a superposition of things at the max. If there's only one thing at the max, that's it. But at any other point, it outputs superpositions of things near the achieved value.
Well, I'm sorry, can you go back?
Sure.
This is just one clause. In the C, UC is C.
No, C is the sum over all. No, C is the sum over all clauses. C is the sum of all the clauses. Okay, C is the ultimate cost function made as a sum over individual clauses.
Gamma is a single number?
A single number for the whole clause, yeah. I have one gamma for, say, yep. And there's only one beta, yep.
This looks vaguely adiabatic to me.
It does.
And so in the adiabatic theorem, there would be the catch of the shrinking gap.
Yeah.
Is there a counterpart to that?
Well, we're going to see that I'm going to have very interesting results at p of 1 or 2, in which the analogy to the adiabatic will not be helpful. So let's do that later, because I'm going to talk about p equals 1. And p equals 1 does not look adiabatic.
No, it doesn't.
Okay?
Yeah.
So I'm going to talk about p equals 1. So now, let's think about this as a variational algorithm. As a variational algorithm, that means that you fix p, and you start with angles gamma and beta, and then you use the quantum computer to make the state, and then you make that state, and you measure a string z, and you calculate c of z, the cost function of z. That you can do classically once you have the string. Now, you can then repeat this with the same angles over and over, and then you'll get an approximate value of f of p, the expected value of the cost of the quantum cost function in the state. Then what you might do is have an outer loop which changes the angles in some way and tries to go uphill. And this is a prototypical variational quantum algorithm where you have parameters and you run a quantum algorithm, it produces an output, then you come back and you change the parameters in an attempt to improve. And people talk about something called VQE, variational quantum eigensolvers. That's in the same spirit, where you have control parameters and you set them in an external loop. So this is the prototypical approach for optimization. And your goal here is then to find new angles to get that. But it turns out that at the shallowest depth, in fact, for fixed p, we can classically prepare and determine the best angles in advance. And I'm going to show you this by example. I would like to consider max cut on a 3 regular graph. Now, max cut is this problem. You have a graph, and it's 3. I'm going to only look at 3 regular, but not for any good, only because I want to. But this is a 3 regular graph, and it's big and stuff. And max cut says, let's assign to the vertices of the graph +1s and -1s with the property that the number of edges whose vertices at the two ends disagree is maximized. It's called a cut because you're really dividing the graph into two pieces, those with the pluses, those with the minuses, and the edges across are called a cut. But this is a prototypical problem and if you can solve max cut, you can solve many other problems. We're not going to talk about solving max cut, we're going to talk about getting a good approximation ratio. So, and those little brackets over there, that means J and K label the vertices, and bracket JK means an edge in the graph. So I'm summing over all the edges in the graph, and my cost function, CJK, is 1/2 minus ZJZK plus 1. And the reason you can see that's right is because if ZJ equals ZK, then you get 0, and that's the sad assignment. The happy assignment is when they're opposite. Okay? So the cost function for max cut in terms of the z's can be written like that. Now, just to be clear, like if your graph is a triangle, you can't perfectly assign plus and minus ones to satisfy all the edges. This thing is called frustrated. And that's a simple example of a graph that cannot be completely satisfied.
It's identical to the Ising, right?
What?
It's identical to the Ising Hamiltonian.
I guess it is a classical icing on an arbitrary graph. Yes. Mm-hmm. So let's look at p equals 1, and let's look at the contribution to the edge jk from the clause j. I'm only going to look at the ZJZK piece because the rest of it is just coming along for the ride. Okay, the 1.5. So look at that object there. And so here it is. We're going to evaluate this. And S is the plus state. Remember I told you that in the beginning? S is the product of the eigenstates in the z direction. All right? So now let's try to evaluate that. So if we look at that, that is simply a rotation of the two quantum operators, Zj and Zk, by an angle beta. But that turns, if you conjugate Zj by that rotation, it becomes cosine 2 beta Zj plus sine 2 beta Yj. And the other one becomes cosine 2 beta Zk plus sine 2 beta Yk. And note, only at this point, only bits J and K are involved. By looking at JK and I do the conjugation with the rotation, I'm still only looking at those two bits. Okay? But now, when I conjugate it with e to the minus I gamma c, remember that's also there, then and if I have, remember that C is the sum over all clauses. So if I have a term in there that does not involve J or K, it just commutes through. Can you see that? So the only thing that matters are the terms in C that involve bits J and K. Okay? Now I have assumed that I have a 3 regular graph. So that means that J and K either have, J has 2 friends and K has 2 friends, but they may not be friends. They're not connected. Or it could be that J and K each have 2 friends, but this friend is in common. Or it could be that J and K have 2 friends and they're both in common. So in terms of what the subgraph looks like, there are only 3 possibilities. Okay, there are only 3 possible subgraphs on this big graph. So that's very helpful because that means that each subgraph type, I can evaluate each subgraph type. And this subgraph type involves 6 qubits. And so there's a function, this is p equals 1. So I only have 1 gamma and 1 beta. I'm doing the shallowest depth. So at p equals 1, I have 1 gamma and 1 beta. But this gives me a function, a 6 qubit thing I can evaluate almost by hand. And I can determine a function of gamma and beta associated with that subgraph type. Okay? Now, I can do the same for the other subgraph types And so on a classical computer, I can evaluate 3 different functions, one that depends on subgraph type 1, tree, one with 1 triangle, one with 2 triangles. And then if I count in the graph the number of edges that are trees, the number of edges that have 1 triangle, the number of edges that have 2 triangles, I can form in my computer, I can sum that up, and then I can optimize that over the angles gamma and beta. Okay, so if I give you an arbitrary graph of an arbitrary size, and I count the number of subgraph types, I can evaluate on a classical computer. And it turns out that on these 3 regular graphs, the p equals 1, the QAO will produce a cut that is at least 0.6924 times the optimal cut. And this is a proof for all instances of 3 regular graphs. And the accomplishment here, you see, is that we actually, this is a worst case analysis. This applies to every graph that you could possibly throw at it. And we're guaranteed to get 0.6924 times all the optimal cut. Now, you know, why is that an achievement in a way? Well, if some of you may know, have heard of the Goldstone-Williamson algorithm, there's if you look at max cut, 30 years ago, a little more, the best classical algorithm for max cut was guess a random string. Now, if you guess a random string, you're going to satisfy half the edges. So you get an approximation ratio of 1/2. Now, what I mean by it's the best possible algorithm, it doesn't mean in practice it was the best algorithm. It was the best algorithm with a provable guarantee of 1/2. Guess a random string is provable because if you guess a few times, you're going to come above 1/2. So then Goldstone-Williamson showed a classical algorithm, which we could talk about, but not here, which achieves 0.878 on any graph. And that was a huge achievement in the world of classical algorithms. So, I mean, had Goldstone-Williamson not existed, our achievement would have been better. But Goldstone-Williamson exists, and we don't beat Goldstone-Williamson. But we still have a worst case performance guarantee, which, and also the other thing is that as you increase the depth, see, I just showed you what happens at p equals 1. But if I go to p equals 2, it'll only do better. And I know the number for p equals 2, it's 0.7 something. And then, but if you go to p equals 3 or 4, it gets too hard to analyze. So I don't really know what happens if I go to very high p, and no one knows. I'm sorry?
Can't you analyze it in a computerized way, proof, enumerate all the different...
Okay, let's tell you what the problem is. Okay, great. No, and I'll tell you why. It's because suppose I go to p equals 2, and then I have to then look at the neighborhood that goes out further. So now the neighborhood is this if it's tree-like. Okay, in other words, at p equals 2, I look at not only this guy's friends, but his friends' friends. And this has 14 qubits, so I can do that. But the next one at p equals 3 has 30 qubits. And so that's I can't put on a classical computer. But you might be able to kill yourself and do p equals 3. But if you go to p equals 4, you have 62 qubits. And so you can't analyze that subgraph. Okay? Yeah. So the computational cost of evaluating the performance of the classical algorithm is independent of n, the size, but grows exponentially in p. So it becomes formidable.
Then it's like one solution that fits all, right?
One set of parameters? I'm going to get to that.
Only for 3 regular, or do you have...
Oh no, I can go other things. I'm just giving an example. Okay, it's just an example for 3 regular. I can do D regular, I can do all kinds of things, but I wanted to focus on something I could show here. So now, are there any questions?
So this is a provable statement.
Yeah.
6.9.
Yeah.
Will you say is the proof easy? Something?
I just proved it. I mean, all I had to do was, of course you have to, no, I didn't prove it, excuse me. I didn't prove it, no. Because if you get an approximation ratio, you have a numerator and a denominator. And I have to get the approximation ratio, if I tell you the number of subgraph types, I can tell you what the quantum thing will do. But now you're going to tell me what's the biggest cut allowed by estimating the denominator. So I can do that as well. If I tell you the number of subgraph types, I can bound the denominator and get the 0.6924.
So the problem is purely local. I don't have to know what's happening at
Right.
infinity.
Right. It's purely local.
There's no classical analog also where for
this?
some sort of an analysis which is also only local in some sense?
Hastings likes to write papers saying that locally, that he has a p=1 algorithm that sort of does what the QAOA does. So, the QAOA is no good. So, but I don't find all that very convincing. I'll tell you another thing about the, ask me about quantum supremacy, because the lowest depth version of the QAOA has quantum supremacy. And so that means it must be quantum. And there's something quantum about it. So at the end, maybe today I'll try to talk about quantum supremacy. Yeah?
Are there any computational assumptions you can make, like about the problem that reduce the number of qubits that are needed to see?
That's a good question. I'm not sure in this case. I mean, 3 regular graphs, I don't know how much more simple I can make it. I could make it tree-like. I don't know what else I can do.
Tree-like, you can just take each level to a different sign, right?
I'm sorry? Yeah.
For a tree-like graph, it's
Oh yeah, but the number of qubits grows exponentially. You see, if I go to p=2, I have 14 qubits. If I go to p=3, I have 30. And that gets much harder for me to computationally deal with on a classical computer. It's independent of n, but it's growing exponentially in p.
Maybe you could clarify what do you mean when we say tree-like?
Tree-like means no loops, no triangles. Locally.
But then it's bipartite.
No, only locally. You don't.
It's only locally.
So
Yeah.
the graph is expanding.
Yeah. What?
So after you found gamma and beta, that's per graph.
Yeah. Well, except in this case, all I need to know is the number of subgraph types. Yeah, and that's it.
Sorry, I just
No.
to distract you a little bit. These last set of questions about tree likeness, they got me thinking. Suppose you have a ring graph.
I know, okay, I can tell you the answer for the QAOA and the ring.
Yeah, I'm just wondering. So max cut. Max cut.
Okay, let me tell.
I apologize.
No, it's okay. I'll tell you the result for the ring. Maybe this will help you. If you have a ring, and this is it. Now, if n is even, there's a perfect cut. So there's a perfect cut. But the QAOA achieves an approximation ratio of 2p+1 over 2p+2. We can sort of prove that. So that's
That answers my question. I
Yeah.
think there's a topological feature here, ring versus line.
well, that's only a little bit at the
It's
end.
in the noise.
Yeah, that's in the noise, because that's a 1 over n effect,
Yeah.
if it's very large. So that's why I said n even. Then it's 2p+1 over 2p+2. Actually, I should take that back, because if you go to p of n over 2, then the neighborhood wraps all the way around, and you see the whole graph, and then the approximation ratio actually jumps to 1. This is only for p much less, this is only for p less than n over 2. But if p equals n over 2, then the neighborhood is the whole graph, and then the approximation ratio goes to 1, which is sort of amusing. Yeah, okay? So let me keep going. Okay, so now I'm just going to tell you a little story, which is sort of amusing to me anyway. It has to do with max E3 ln 2. So let's talk about what problem that is. Here I have a problem. I have n variables, m equations, and each with 3 variables. So I'm going to define a computational problem. I have n variables, m equations, and each equation has 3 variables, and it might be of the form zi plus zj plus z. No, it might not be of the form. It is of the form zi plus zj plus zk mod 2 is 1 or 0. Here, these are bits. They're 0 and 1. So I'm giving you equations, and I'm imagine. So the way I specify the instance is I tell you I have this many variables, n. I have m equations, and each equation involves 3 bits, and they either add to 0 or 1. So the instance is specified by a collection of triples and a 0 or 1 for each one. Now, what's amusing about this problem is it looks like a prototypical NP-complete problem, but I can answer the question, does it have a solution or not? And I can do that by Gaussian elimination. I can simultaneously solve these equations if there is a solution.
I don't understand this equation. This is an identity. Every 3.
No, it's either I'm going to tell you those 3 have to add to 1 or 0. What do you mean?
Pick one of them.
I'm
They
picking
always
the,
add
the,
either to 1 or to 0. So what is
the instance is specified by giving you, I tell you bits 1, 7, and 99 must add to 1. Bits 2, 13, and 44 must add to 0. So the instance is specified by a collection of triples and a 0 or 1. I don't say either one, right? Does this make sense?
Yes.
Okay. Now that is a funny little problem because you can solve that. You can solve if those equations can be solved. You can find the solution just by adding and subtracting. But as my friend Michael Sipser says, algorithms are accidents. They're not of fundamental importance. They're just like things people discover. Anyway, but in this case, you can solve it. But what you can't do, if it's not satisfied, is count the number of the maximum number of equations that can be satisfied. Okay, so I want to go to the I want to assume there are a lot more equations than variables. It can't be satisfied. And your task is to now find a string that maxes the number of satisfied equations. And this is NP hard to find the optimal solution. That means that if you could efficiently do this, you would show that P equals NP. You could solve the traveling salesman. But it's going to get worse than that because we're going to try to find a good solution. So now we're going to look at approximate optimization where we look for a good solution. So in order to do that, one algorithm is guess a random string. That's my algorithm. I just guess a random string. That's going to satisfy half the clauses, half the constraints, because half of them, if you guess it randomly, will be satisfied. That gives an approximation ratio of 1/2. But what's kind of interesting is that if you could get it, if you had an algorithm that in worst case got 1/2 plus epsilon for any epsilon. So I promise you, I give you an instance and you're going to get 1/2 plus 0.00001. I promise it works in all cases. Then P equals NP. So improving the 1/2 to 1/2 plus epsilon is computationally very difficult. So now I can't, so that's really challenging. But now what we're going to do is I'm going to give you a little help. What I'm going to tell you is that I'm not going to consider all possible instances and instances of particular choice of triples and zeros and ones, but rather I'm going to tell you that every variable is in no more than D equations. Okay, so now I've told you something, I've given you help. But if you can do that, then in the year 2000, Hofstad had an algorithm that got 1/2 plus constant over D. In other words, for fixed D. But that doesn't contradict the other thing, because if you think about it, like that has to work for fixed epsilon, and this has to work for any D. So if you make D big, you could go under the epsilon. So anyway, that was Hofstad's algorithm. But then in 2014, in our second paper on the QAOA, we showed that at P equals 1, we could achieve 1/2 plus constant over D to the 3/4, which beats that other thing. So at that moment in time, we had a quantum algorithm with an exponential speed up over the best known classical algorithm at the time. So what happened is that Scott Aronson blogged about it and said there's this really nice new quantum algorithm, and the computer scientists had a conniption fit and decided they couldn't live with that. So they kind of took something we taught them and got a classical algorithm, got 1/2 plus constant over D to the 1/2, which did beat us. But I will say that that team of computer scientists was very formidable. And there was those 11 people who got together and beat us up. There were 3 of us and 11 of them. Anyway, so any Israelis? Well, Boaz Barakano did Ragav, yeah. Yeah, okay, a couple, right. It's like the whole United Nations got together and conspired against us. Anyway, they did beat us.
But you could still find an EQP algorithm to, I mean, the P equals NP statement, would you finding a quantum algorithm sort of imply that or no?
Oh, well, let's talk about that in a second, yeah. Well, so anyway, I forgot to mention my collaborators, Jeffrey Goldstone and Sam Gottman, who, Goldstone is the same guy as Goldstone bosons, if you ever heard of a Goldstone boson. That's my collaborator. Anyway, I forgot to mention them, so sad. Anyway, I went to high school with Sam, so I know him forever. So anyway, we improved our analysis, and we got a half plus 1 over. We didn't change the algorithm, we just improved the analysis. And we were able to get a half plus 101 d to the 1/2 log d, but we still had the log d. You know, so we're still not as good as the classical, provably. But we could also show that if you took random instances, we got a half plus 1 over 2 square root of 3e. E is Euler's number, d to the 1/2. So on typical instances, we can do that. But the question is, can we get rid of the log d in the worst case? It turns out that if there exists an algorithm that gets a half plus constant over d to the 1/2 for a sufficiently large constant, then p equals np. So, you know, that's quite a challenge to see how well we can do. So obviously, the algorithm of those 11 people, the constant was less than the threshold required to show that p equals np. And I don't really know how the quantum algorithm does if you go to p equals 2. I don't even know. So, okay, so I was going to go to typical performance, but maybe, well, first of all, are there any questions? Yeah, sure.
So what, previously you showed us an argument why the 1 over d doesn't contradict with the
What to the epsilon thing?
p equal np. The same argument applies to d to the half.
This is a stronger statement. You're saying that if there exists, before I said if there exists an algorithm with a half over constant epsilon for a fixed epsilon, p equals np. Now I'm telling you if there exists an algorithm with a half plus a big constant over d to the 1/2, then p equals np. Those are different statements.
That could make the absolutely arbitrarily large and make the remainder term smaller than any epsilon.
But those are they're different things. Right here, forget the epsilon thing. I forget that for a second. Now I'm just telling you, I mean, I don't see the contradiction. They're different things, right? In one case, I have a half plus a big constant over d to the 1/2 for any d, and
In the epsilon thing, you can take any d you want.
yeah.
In the epsilon thing, you can take any d you want.
And what about
And here you can take any d you want, but this constant.
You have to have a big constant upstairs.
Whereas
Yeah.
in the epsilon, it is constant. It
Yeah.
stays good.
so the constant is dependent on d.
No.
Here, no.
No. The constant's a big number.
But fixed.
Yeah.
So now I take d much larger than that.
Yeah. So. No. So what do you mean?
You want a big constant. You want 1 plus this thing to be as big as possible.
I'll get a private tutorial.
Okay. Fine. Anyway, that's sort of the so what? Anyway, the lesson here is that the QAOA at shallow depth can be analyzed, and we can have worst-case performance guarantees, and there are tons of other problems you could apply it to and has been applied to. You can go to higher depth, you can do whatever you want. But there's a lot of complaining that the QAOA is just a classical algorithm or something like that. So I just want to tell you that it also has quantum supremacy at p equals 1. And let's see what that means technically. Quantum supremacy says that if you have a circuit, it says that if you have a quantum circuit which you've described in some fashion, and you start with this, so you have a unitary operator, you start in some initial state, I don't care what it is. Let me just call it 0, meaning all zeros. And then you have a quantum computer, you hit your initial state with U, and then you measure in the computational basis. And you measure a string Z. Then you're going to get the string Z with this probability, P, I'll call it P quantum of Z equals this. Okay? And now, if you run a quantum computer and it starts spitting out strings, it's necessarily giving you strings with that probability, because that's what it does. So now you can ask another question, which is, suppose I had a classical computer with a random number generator, and I take the classical computer with a random number generator, and I write code, and I want that code to have the property that when that it spits out strings, because it's a random number generator. At the end, it has a Z. But I want it to spit out strings with a probability P from the classical computer of Z, which is very near this. So I have a description of the unitary, a compact description. I write code, and then I say, with my random number generator, I'm going to do this. Now, suppose that, now I can't remember, but suppose that, P of Q of Z minus PC of Z, the magnitude of this is very tiny. But don't ask me what I mean by that, just very small. Just, it's really, really small, even 0, or some tiny amount. Well, if you could do that, then the polynomial hierarchy would collapse at the third level. And that is the statement of quantum supremacy, which they attribute to the Google quantum computing effort. It's the statement that the it's kind of unfair, because the quantum computer can't help but output strings according to the unitary which it has. But the statement is that object those probabilities cannot be reproduced by a classical computer. And we can talk about the significance of that or not, but that is the claim of quantum supremacy, which is sort of, you can't really prove anything asymptotically by being at a fixed size, and Google's quantum effort was at 53 qubits, but let's say that that is a very difficult computational task. Well, it turns out that the QAOA, and this is a worst case result, this has to work for any circuit. And then part of the Google effort was to show that, it was really happening even though the circuits looked like random. They came from a random distribution. But it turns out that if this is just, U of gamma beta, U of the QAOA circuit as a function of gamma and beta at p equals 1, that in worst case, you also have quantum supremacy. In other words, the output of the QAOA at depth 1 cannot be reproduced by a classical computer unless the polynomial hierarchy collapses. And it also turns out that you can ask about the assumptions that there are things that people like to say about typical instances. And typical means that the circuit that, let's say, the Google guys run has a sequence of unitary operations, and each individual one is seen to be random, so the whole thing is seen as a bunch of random ones. And it turns out that the same assumptions that you can use to prove supremacy under that assumption apply to the QAOA at depth 1 if I just have an arbitrary cost function upstairs. So the reason I'm emphasizing this is it means in some sense that I think the QAOA cannot be accused of being classical, because otherwise it couldn't have quantum supremacy. That doesn't mean it's useful. I'm not saying it's useful, but I'm saying that at shallow depth we have worst case performance guarantees, and it is quantum because of supremacy. Does that make sense? Okay, more questions, please?
You said that you choose one single gamma and beta for all the gates, for all the gates within a layer.
Yeah.
You said
Oh, why do I do
explain
that?
why.
Yeah, well, you know, suppose I had, suppose I allowed a different rotation for each spin. And now suppose I had a very difficult problem, some kind of NP-complete problem, and I allowed a different rotation for each spin. Then I could rotate those spins to the solution. So if I give it enough freedom where I can rotate every single spin by a different amount, then suddenly in my I have in that when I'm looking for parameters, I'm also searching over the parameters that find the best solution. So I've just sort of made it. I've given the quantum computer too much power, and I've lost my ability to analyze it if I have a different rotation for every spin. Does that make sense? You see, you don't want your quantum computer to say, well, at the first layer I can just rotate my spins to the solution. Because then I could just say that's the same as the original problem, which is find the string. So I don't want to do that. That was sort of an answer to your question. Yeah, it's from a variational point of view, it's more liberating to have more parameters. But if you have so many parameters that you can just rotate to the solution, then the problem of finding those parameters is the same as the original problem. So that's too much. And it's kind of remarkable to me that the QAOA works with parameters that are the same for all the spins and the same for all the clauses. It still works. I don't know why that is.
I heard a recent talk where Lolita Alonov made a statement that for boson sampling in a noisy circuit,
Oh, yeah.
it can be sampled with an polynomial.
Yeah.
Is it the same?
I don't know. I absolutely haven't looked into that. Yeah, there are statements, I think Dorit, Aronov, I think Umesh Vazirani. I don't know if they're on the same paper, but yeah, they are. Okay. They have been claiming that, if there's noise in the circuit, it makes it easier to sample. But also, even the okay, the answer is I don't know if that applies. Probably, because almost everything that you say about supremacy for random circuits at high depth applies to the QAOA at depth 1, where you allow an arbitrary cost function.
It would be the same for any quantum pattern.
I can't say that, because I haven't read the paper. I don't know. I'll ask Dorit when I see her.
When you say arbitrary cost function, you mean I can choose any, or I should randomly pick many?
Well, okay, so there's a difference between worst case and random, okay? So the original supremacy statements are worst case. But then people wanted to argue and the proof that, I should have said the proof was by me and Aram Harrow, that the QAOA has supremacy at depth 1, that's worst case. But then you can ask another question, which is, I don't really care about worst case. I care about random instances. And one of the big claims of the supremacy experiment of Google was that they were choosing the parameters in the circuit. The circuit consists of a bunch of gates, and they were choosing those randomly, so it consisted of a sequence of random gates. But then the claim was that you could show that was as hard as worst case. Okay? That was the claim. But that's subject to an unproven assumption. So subject to an unproven assumption, average case is as hard as worst case. Now maybe that assumption is true. But exactly the same set of logic applies to the QAOA. If you prove it in worst case, then you look at what you need to show in typical case, and subject to the same assumption, the QAOA has supremacy in typical. I don't know, does that answer your question? Okay. Okay, well then ask me later. Thank you.